Hello, everyone, and welcome back. In the previous two videos, we introduced power series. These are infinite sums of functions. In particular, they're infinite sums of powers on x. Now, what I kept talking about while we were going through power series is I was saying we have a new way of representing functions, right? This is kind of a cool new thing where we can represent functions as infinite series, but this comes with the drawback that they are, defined locally. You only have conversions on some maybe small set or some open interval, as opposed to what you're used to, where they're sort of defined everywhere, like sine of x or e to the x or just x squared. Now, one of the benefits of using power series is that differentiation is super easy because it's just differentiating polynomials. Integration, again, super easy because it's just integrating polynomials. Now, here's the issue. What we've seen so far is that I have just given you a power series. I say, what is this? What is the function it's describing? Now, this is not a good way to go about your life, right? You don't want to just be feeling around blind in the dark, just hoping that you're describing a function that you actually care about. You obviously want to go the other way. You want to say, if I have a function, how do I describe it as a power series? And that's what we're going to talk about today. That's what we're going to get into. And in particular, we're going to talk about what are called Taylor and Maclaurin series that help us to expand functions in terms of these power series. So let's take a look. I want to start by briefly sketching out an idea here. Okay, so first of all, imagine I have a function described by a power series. So if I've got f of x is equal to, so an infinite sum, an x to the power of n. So actually, let's do x minus a to the power of n, just to keep it as general as possible. So it's a power series centered at a, could be any value. Clearly, if you just expand this thing out, it's a constant plus the linear term plus the next quadratic term plus the cubic term. And I'll put the quartic up, and then we'll just do a dot, dot, dot after that. Okay, now what we saw last video was that if you take a derivative here, it's the same as just differentiating every single term. So you get f prime of x, and this now gives you a1 plus 2a2 x minus a plus 3a3 x minus a squared plus 4a4 x minus a cubed, and so on and so forth. And let's have a little bit of fun. Let's take one more derivative, or let's take another derivative. So I get the a1 goes to 0, and I get 2a2 plus, now I'm going to write this as 2 times 3 times a3. So I don't want to make it into a 6 because I want to be able to see a pattern. And then this becomes x minus a, and then 3 times 4 times a4, x minus a squared, and so on and so forth. And let's do one more derivative just to see the pattern. I get 2 times 3 times a3 plus 2 times 3 times 4 a4 x minus a, and there's more, but that's okay. Okay, so what was the point in me doing that? Well, actually, we can use this to figure out what these coefficients are. So first of all, we know that if you do f of a, if I put that into my series above, if I just underline, this term disappears, this term disappears, this term disappears, this term disappears, and every higher order term disappears. So that tells me f of a is equal to a0. Okay, maybe not that exciting, but it's still important. But similarly, if I do f prime of a, the same principle applies here. So then this bracket disappears, this bracket disappears, this bracket disappears, and they keep disappearing all the way up. And that leaves me with a1. And then if I do f double prime of a, same idea. I get 2a2. And f triple prime of A is equal to 2 times 3 times A3. And so now what you could do is you could pause the video and you can try and figure out what the pattern is, right? So if I ask you what the fourth derivative at A is going to be, well, based on the pattern, it's going to be 2 times 3 times 4, A4. And the fifth derivative at A is going to be 2 times 3 times 4 times 5 of A5. And in general, if you take the nth derivative of of f and evaluate it at A, you get n factorial. So 2 times 3 times 4 times 5 all the way up to times n times an. And you can rearrange this so that you can actually say that an is equal to the nth derivative of f evaluated at the point where you are centering your series around, divided by n factorial. And so really, this tells you, or this gives you an explicit form for your series. So if I wanted to find the series of my function, f of x, whatever it happens to be, and I want to locate it around some point A, well, if I want to figure out what these coefficients are that make my series, then I just need to take some derivatives, right? So that the nth term is going to be the nth derivative at A divided by n factorial. Now, this is what's called a Taylor series. So let me give you a little definition here. So let f be a function with derivatives of all orders. So I need to be able to take a derivative of every single order, because you can see that I need infinitely many, like a sub n terms, and that means that I need infinitely many derivatives. So with derivatives of all orders throughout some interval, containing A in its interior. So you're gonna, you can take derivatives along some interval, and in the interior of that, you have your point A that you're gonna focus this around. So then Taylor series, so named after a British mathematician, Taylor, a Taylor series of f at x equal to A is given by, well, this is exactly what we just proved. So this is f of x is equal to the sum from n equals 0 to infinity of the nth derivative at A divided by n factorial, and then times x minus A to the power of n. So all this is exactly what I just showed you with that informal derivative taking and finding the pattern to get the coefficients. Now, some people also refer to what's called a Maclaurin series. So this is named after a Scottish mathematician, Colin Maclaurin, I believe his name is. So the Maclaurin series of f is the Taylor series with A equal to 0, which is, f of x is equal to the sum n equals 0 to infinity, the nth derivative at 0 divided by n factorial x to the n. Right, so of course, centering this thing around 0 is so important. We saw it with the power series as well. It adds to like a simplification with at least our analysis here. This has its own special name. We refer to this as the Maclaurin series. Now, throughout mathematics, most people don't use the term Maclaurin series much anymore. We typically just use Taylor series, because Taylor series contains the Maclaurin series as well. So you'll hear a lot of people say Taylor series. You won't hear a lot of people say Maclaurin series anymore. But this is cute, right? This is a cool little fact about how we can expand these things out. So let's do it. Let's put it into practice. So let's say let f of x equal to 1 over x, and find the Taylor series at a equal to 2. And we can, once we do this, we can ask ourselves where this thing converges. But let's first find some derivatives. So first of all, if f of x is equal to x to the minus 1, f prime of x is equal to minus x to the minus 2, f double prime of x is equal to 2x to the minus 3. So what you're going to see as you work through problems of finding Taylor and Maclaurin series is you're going to be looking for patterns. So the third derivative of x is equal to minus 3 times 2x to the minus 4, and so on and so forth. And I think I have enough here to find a pattern. If you don't, keep taking derivatives, keep looking for that pattern. But in general, the nth derivative of this function is given by minus 1 to the n. We alternate between positive and negative, times n factorial. That's the 3 times 2. And it could be, 5 times 4 times 3 times 2 if you're going to do the fifth derivative. X to the minus n plus 1. And this implies that if I evaluate this at a, I am going to get, so I have minus 1 to the n times n factorial, and then 2 to the minus n plus 1, which I can clean that up just a little bit. I get minus 1 to the n times n factorial divided by 2 to the n plus 1. And so if I do my Taylor series, remember the Taylor series looks like this. I have the nth derivative at 2, which is a, divided by n factorial. So you can see n factorial coming from the nth derivative. It's going to cancel with the n factorial in the denominator. And so I get a nice series representation of the form minus 1 to the n divided by 2 to the n plus 1 times x minus 2 to the n. And finally, we're going to ask ourselves, where does this thing converge? So where does the series converge? Well, in this case, it's a geometric series. The initial term is 1/2, and the ratio, so maybe I should write this down. It's a geometric series. And the ratio is equal to minus x minus 2 over 2. So to go from one term to the next, you multiply by negative x minus 2 divided by 2, which implies convergence when minus x minus 2 over 2 is less than 1, which you can just rearrange to see that this is when x minus 2, is less than 2. Which, if you want to open that up, this is equivalent to saying 0 is less than x, which is less than 4. And that kind of makes sense, right? So look again at the original function that we started with. We started with 1 over x. So 1 over x is not continuous at 0. So that kind of puts a limit on how far we could actually expand this thing, because I can only have a series representation where I'm continuous, where I actually exist, where I can take derivatives. And so what this radius of convergence is representing is the fact that I can get as close as I want to 0 without actually getting there. Now, the last piece of this is, because this is a geometric series, you could actually confirm that this series, in fact, is equal to 1 over x when it converges. You can just do that using the sum of a geometric series. So I'm going to omit that because we kind of know this from from the Taylor definition here. But nonetheless, you can check it to make sure that things make sense. Okay. So here's something else that I want to point out that's really, really cool about this. What do we know about series? Well, series are good. We can use them as approximations for infinite sums by just truncating the series. So if we just add up the first n terms or something like that, since we know that this converges, we can approximate the function f of x using a polynomial. That is very, very weird, right? This is a cool thing. This is what's known as Taylor's theorem. But basically, if we only add up the first maybe 100 terms of this of these Taylor series, we have a polynomial approximation of our function. So again, look at what we said right here. The function 1 over x can be written as the infinite sum here. Now, infinite sums in practice are not particularly useful, but you could take a finite sum here, so just add up the first 100 terms or so, and now you've got a polynomial approximating the function 1 over x. And the approximation comes from the fact that it's not an infinite sum anymore. And there's another aspect of this, is that it's a local approximation. You are not approximating the function everywhere. You are approximating the function near to. So that's why we always have a center to these Taylor series. So let me give you the proper definition of everything that I was just talking about. And this is what's called a Taylor polynomial. So let's say, let f be a function with derivatives of order k for k equal to 1, 2, ... up to n. So the idea here is that you can take up to some number of derivatives of your function. You don't need it to be infinitely differentiable in some interval containing a as an interior point. So the same pieces that you needed for the Taylor series, containing a as an interior point. Okay, then for any integer n from 0 through capital N, so up to the number of derivatives you can take of this function, and let's put this in red to emphasize it, the Taylor polynomial of order n, so little n, generated by f. So there's a lot of there's a lot of writing here before we can get to the actual math. At x equal to a is the polynomial. So let's take a look at this. So my polynomial is, I'm going to call it P for polynomial, sub n for the order of this polynomial. This is equal to f of a, and then plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed. And you keep doing this until you go all the way up to the nth term.
So you go the nth derivative at a divided by n factorial x minus a to the n. So all that you did is you chopped the infinite Taylor series off at some number n. And what's the result? Well, the highest power on x here is potentially x to the power of n. So you got a polynomial on your hands now, right? It's not an infinite sum, it's a finite sum. So this is a genuine polynomial. And so we can use this to approximate functions, right? If the original function is the infinite series, we truncate that thing and we've got a finite series. So maybe you might be asking yourself, sometimes how does how does a computer calculate sine of 3? I don't know how to do it, right? I know that 3 is close to pi, so this thing should be close to 0, but I don't know what the value should be. Well, it turns out that you can do this using these Taylor polynomials. So let me give you an example. Let's take a look here. Let's find the Taylor series and the Taylor polynomials. So the Taylor series plus polynomials generated by f of x equal to e to the x at x equal to 0. Okay, so again, this is a weird one, right? E to the x. Sometimes you might ask yourself, how is your calculator figuring out what e to the power of the square root of 2 is? Well, it can do it using these Taylor polynomials. So let's first note here that since every derivative of this function is equal to e to the x, this implies that if you evaluate all of the derivatives at 0, you always get 1 for every n greater than or equal to 0. So therefore, f of x equal to e to the x is equal to the sum of n equal to 0 to infinity of 1 over n factorial x to the n. Which, if I want to write that as a proper fraction like this, it's not really adding anything, but this might jog something in your memory, right? We actually looked at this power series in the previous video, and we saw that this thing converges. So this converges for every x in R. Right? We proved that in the previous video. And so now we know that it converges to e to the x for every single R. So you want to figure out what e to the 100 is. Well, you can put it into this series. You put x equal to 100 into the series. And so the Taylor polynomials, so let's write out the first few. The Taylor polynomials, well, the linear approximation, so the Taylor polynomial of order 1 is equal to 1 plus x, right? That's just the first 2 terms of this sequence. The second one is 1 plus x plus 1 over 2 factorial x squared, which is just 1 plus x plus a half x squared. Similarly, if I want to do P3, I get 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, which gives me 1 plus x plus 1/2 x squared plus 1/6 x cubed, and so on and so forth. And if I wanted to do Pn, this is an n degree polynomial, which is going to look like this. X cubed plus 1 over n factorial x to the n. Now, why is this awesome? Because, again, this is how you approximate things. I can set up a computer program that can evaluate or that will build my Taylor polynomials up to any order, right? This is just a for loop or a recursive process. And I can put in a value of x into that. Maybe it could be x equal to 100. It could be minus pi. It could be the square root of 2. And that will approximate e to the power of whatever that number is that I'm interested in, e to the x. That's how, or that's one method by which, a calculator is actually giving us values at these functions that are not just simple functions like, say, a polynomial. And it's using polynomials to do it. This is super cool, right? I think this is an incredible way to view functions, is through these Taylor polynomials and through these Taylor series. Okay, let's keep going. Let's have a little bit more fun. I mentioned trigonometric functions earlier. Let's do one. Let's do the same thing. So same process for f of x is equal to cos of x. And again, I'm going to do this at x equal to 0. Okay, so here's the thing. Cos has a little bit more involved derivatives. So if the original function is cos of x, then f prime of x is equal to minus sine x. And f double prime of x is equal to minus cos of x. And f triple prime of x is equal to sine x. And this thing will repeat itself, right? So eventually I get back to where I started. And so it's cyclic. And in general, I can say that if I take an even derivative of this thing, this is just plus or minus cos of x. Okay, so minus 1 cos of x. Again, the big thing when you're doing Taylor series is, finding the pattern. So I'm only going up to 4 derivatives to look for the pattern. You might have to go to more. That's okay, right? It takes practice. And so similarly, the odd derivatives are plus or minus sine. So I get this. And so at x equal to 0, we have, well, what do we have? We have that the even derivatives, sorry, that should be at 0 now. The even derivatives are equal to minus 1 to the power of n, and that comes from the fact that cos of 0 is equal to 1. And the odd derivatives all vanish. And that comes from the fact that sine of 0 is equal to 0. So therefore, my Taylor series, f of x, is equal to, if I just write out the first few terms here, this is f of 0, which is equal to 1, plus f prime at 0 divided by 1 factorial, so divided by 1, which is 0 times x, plus f double prime at 0, which is minus 1, divided by 2 factorial times x squared, plus then the triple prime, so that's an odd derivative, so that's 0 over 3 factorial x cubed, and I can keep this going. I have 1 divided by 4 factorial x to the 4, blah, 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 blah. And it takes a little bit of work, but you can write this thing compactly as the sum from n equal to 0 to infinity of minus 1 to the n. That is my alternating even derivatives, flipping back and forth between positive and negative. X to the even power 2n divided by 2n factorial. And here's the exciting thing. If I wanted to, I could figure out, I can use finite approximations of this thing in order to approximate cosine of any value. In fact, I'm going to leave this as an exercise for you, but the radius of convergence is everything. So converges for every x in R. So you can check that using the ratio test. It's a really nice application of the ratio test, and you're going to see that this thing converges to cos for every single x. So you can approximate the cosine function using this, using these Taylor polynomials. And similarly, the Taylor polynomials, so let's say P1 of x, well, this thing is just 1 because there's no linear term, right? It's 1 plus 0 times x, which is just 1. But then P2 of x is 1 plus 0 times x minus 1/2 x squared, which is equal to 1 minus x squared over 2. Similarly, P3 of x, this is 1 plus 0 times x minus 1/2 x squared plus, well, it doesn't matter if it's plus or minus, 0 over 3 factorial x cubed, which is equal to, again, 1 minus x squared over 2. Let's do 2 more just so you can see the pattern. So the fourth order Taylor polynomial, this is 1 plus 0 times x minus 1/2 x squared plus 0 over 3 factorial, and then plus 1 over 4 factorial x to the 4, which, after knocking off all of the even terms, or all of the odd terms, 1 minus x squared over 2, and then plus x to the 4 over 24, which is 4 factorial. And finally, I'll do P5. Well, because there's no odd terms, there's going to be no fifth element, which means that this is equal to just the even up to the order 4 approximation here. Now, just to emphasize something, you've probably seen, or you've probably heard people say that cosine is an even function, right? We know what even functions are. They have a symmetry over 0. So you can mirror them over the y-axis. They're exactly the same. And we know that polynomials with only even powers are even functions. Well, now we can see that this property is reflected in the Taylor series, right? Look at the Taylor series here. It only has even powers. So that makes sense, right? Because we know cosine is an even function. Similarly, sine is an odd function, right? F of minus x is equal to minus f of x, that odd function property. And so what do we expect? Well, if I do a Taylor series for sine of x around x equal to 0, it should only have odd polynomials in it. So you can go ahead and you can try that as an exercise. You should be able to follow this process that we just laid down for cosine in order to see that the sine expansion only has odd powered polynomials. Okay, let me conclude with one just super weird example. Okay, I want to show you where this kind of can break down. And let's let f of x, so this is a truly awful function that we probably wouldn't encounter in this class otherwise, but I want to show it to you because I think it's super cool. It's this function. Okay, so technically it has a singularity at 0, but what happens is you sort of informally 1 over x squared goes to infinity as x goes to 0. And then you have e to the minus infinity, which goes to 0. So this thing should make sense. In fact, it does. It takes a lot of work, and I do not expect you to recreate it. I just want to show you this because I think it's cool. We have the nth derivative at 0 is equal to 0 for all n greater than or equal to 0. If you want to try and prove that, it's just L'Hopital's rule. So try it with the first derivative. Try taking the first derivative of the function e to the minus 1 over x squared, and then use L'Hopital's rule to find the limit as x goes to 0. But here's the issue, right? The Taylor series is Okay, well, what's the Taylor series? Okay, it's like f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. Actually, let's do one more in there just for the sake of it. Triple prime of 0 over 3 factorial times x cubed. And I'm centering this around x equal to 0. But obviously you can probably see what's going to happen, right? 0 plus 0 times x plus 0 times x squared plus 0 times x cubed plus ... which is equal to 0. So what does that mean? Does this thing not have a Taylor series? No, it has a Taylor series. Just locally, this thing looks super, super flat. So in fact, if you sketch out what this function looks like, I haven't had a sketch in a while in this class. If this is x and this is y, in fact, this function sort of looks sorry, the left-hand side didn't look very pretty, but the point is, this thing looks very, very, very flat right around 0. So this is, let's say y equal to f of x. And so what is the Taylor series telling you? It's telling you that this thing looks basically like a constant function. It looks like the constant function 0 when you sort of zoom in around here, right? That's what a Taylor series is doing. It's telling you to zoom in because it's a local description of the function. And that tells you that the Taylor polynomials, well, the Taylor polynomials are Pn of x. Everything is just equal to 0. So what this is telling you from a computational standpoint, if you're doing this on your computer, it says, okay, you want to approximate that function near 0 using Taylor polynomials? Well, then just write 0. Right? That's essentially what it's telling you. It's saying there's no point. You can't do it with polynomials. They're not going to be helpful. You want to approximate what happens when you put x equal to 0.1 into this function. It's basically 0. That's all that matters, right? That's what this is telling you, is that this function is flat. There is like nothing going on at 0. And I tried to draw that in my figure here, but it's not perfect. But nonetheless, most examples are not going to be degenerate like that one is. Most of them are going to be like our cosine or our e to the x example or our 1 over x example, where we can do these sort of local descriptions using Taylor or Maclaurin series in order to better understand a function just using polynomials. And in particular, it's through these Taylor polynomials that we get our numerical approximation of very, very complicated functions. For example, sine of e to the x squared. That is a very, very complicated function. It's very hard for me to figure out what happens when I put x equal to 2 into it, for example, right? That's sine of e to the 4. I have no idea what that number is, right? But what I could do is I could find a Taylor approximation of this thing. And then I can use the Taylor polynomials that come from the Taylor series in order to get a polynomial approximation of this function. That's the point, right? It's really, really awesome in that regard because we can use polynomials to understand functions that are ridiculously complicated.